Today's lecture on the CTFT is about Parseval's relation. So we will define or talk about Parseval's relation and also define the concept of a DC component and give some examples. Parseval's relation at a high level is saying that the energy of the signal is the same whether you compute it in the time domain or you compute it in the frequency domain. So here, if you're working with the omega, with the angular frequency, then you have to adjust the units by a factor of 1 over 2 pi. Or if you work directly with the frequencies, the energy is the same. So both in the frequency and in the time domain. As an application to Parseval's relation, let's try to find the energy of the signal x of t equal to sine 3bt divided by 2t. So b here is a constant. So if you want to do it directly, you'll have to find the energy here, which is equal to the integral from minus infinity to plus infinity to the magnitude of sine 3bt divided by 2t squared dt, right? So this is how you're capturing all the energy. By the way, this should look something like this. So it's a sine, but it gets amortized because you're dividing by the factor t here. So as t goes to infinity, this is going to go to 0. And of course, you can do this integral, but we're trying here to find an easier way to find this energy by using Parseval's equation or relation. Now, to use Parseval, we have to find the CTFT of this signal in the frequency domain and then find the energy there. And the hope is that the signal or the CTFT will lead to an easier integral to compute. Now, the question is, what is x of j omega here? What is the CTFT of the signal? Now, if you look at it for a second, you see it's not immediately something you've seen before, but it's very similar. Because we know that it looks like a sinc function. And recall the CTFT of the sinc function, which looks something like this. So you have sine bt divided by pi t, which is if you want to think of it also as the impulse response of a low pass filter. Then in the Fourier domain, it's going to look something like this. So it's a low pass filter that only lets frequencies between minus b and plus b go through. So it's a box function and of magnitude 1. And this is what I want to use next to find the energy of the signal that I'm given. So the signal we are interested in, x of t, which is this here, I can try to bring out of it the sinc function. So it's going to be sine 3bt divided by pi t. And this part here I know how to deal with, times a constant, which will be also easy to deal with. So I know that the signal, so if I call this part here, if I call it y of t, then I know that the energy in x is equal to the energy in y times the constant square, because again, in energy you're squaring everything. And like I said, yj omega is the box or the low pass filter. So the bandwidth here is 3b, so I have minus 3b and plus 3b. And the amplitude is 1. Now to find the energy here by using Parseval's, since I'm doing things in the omega space, so I know that the energy of y is equal to 1 over 2 pi, the integral between here minus 3b and plus 3b, 1 square d omega, right? So this is going to be equal to 6b divided by 2 pi, which is equal to 3b by pi. And now I can compute E of x, which is pi squared by 4 times 3b by pi, and I'm going to get the energy of x to be equal to I can simplify here, so it's going to be 3b pi divided by 4. And you can easily see that computing this integral here is much easier than computing the integral of the sinc function of sine t by t. So in that sense, sometimes the Parseval's relation can be handy. And the slides here gives a more detailed derivation of the results. Now I want to move to another concept, which is the DC component. So the DC component is of a signal is the frequency component at frequency equal to 0, at omega equal to 0. And we call this the DC component. And we usually find it by evaluating x of g omega at omega equal to 0. And if you plug in this in the formula, so it's the integral between minus infinity and plus infinity of x of t dt. So it's the component is the magnitude of the signal at frequency equal to 0. So the DC component is the CTFT at frequency equal to 0, and you can compute it by just integrating the signal x of t. And it's called DC component because it's the magnitude of the signal at frequency equal to 0, so there's no frequency. So it's like a direct current versus an alternate current. So it's just referring to that analogy. Also, if you can, so here you're finding x of 0, the CTFT. Also, if you have the CTFT and you want the value of the signal at 0, you can also compute it following this formula. For instance, what is the DC component of the sinc function or a low-pass filter? Of course, here you could just do the integral like we did, or like we tried to do before. So you can say, well, the DC component here, DC, it's equal to the integral of x of t dt. By the way, this is not the energy that we computed, because of the energy you need to have this square, right? Now, again, you could do this integral, but an easier way to do is to find the frequency, the signal on the frequency domain. So it's a box between minus b and plus b, and magnitude was 1. Then I know that x of j0 is equal to 1, and this is the DC component of the signal. And the details are done here. So again, you get that the DC component is equal to 1.